Hello students, in this session we will discuss direct and bending stresses in a column section. In a previous session we discussed what is direct and bending stresses. So basically when a column section is subjected to eccentric type of the load, direct and bending both type of the stresses will be developed in a column section. Basically column section is designed to carry compressive type of the load, and generally we are expecting that the stresses developed should be compressive in a nature. So in this session, first of all, we will discuss no tension condition. After that, we will discuss core or kernel of the section, and then we will discuss core or kernel diagram of different cross section. So let's start with no tension condition. Here, the given column section is subjected to eccentric load P and eccentricity is small e. Now what is eccentricity? So eccentricity is the distance between line of action of this load and axis of the member. Now because of this eccentric load, face CD of this column section will be subjected to maximum stresses, which is equal to sigma 0 plus sigma b, which we discussed in previous session. Now, so we can say that stresses developed on face CD will always be compressive in a nature. Now, due to this eccentric load, face AB of this column section will be subjected to minimum stresses, which is equal to sigma 0 minus sigma b. So, in case if direct stresses developed on face AB is less than bending stresses developed, then face AB will be subjected to tensile type of the stresses. And while designing column section, we should avoid such condition. So, here are two basic conditions that we will follow to maintain no tension condition while designing column section. So the first condition is that load must be within E limit. Now what is this E limit? So E limit is a eccentricity or the limit of eccentricity if within which the column section is subjected to eccentric load, then there will be no tension in a column section. Now, second condition, sigma minimum should not be negative. It means sigma minimum should not be tensile. Okay, so here we also discuss it. Face AB will be subjected to sigma minimum. And for no tension condition, we need to design a column section in such a way that sigma B should not be negative. Okay, so sigma minimum is equal to sigma 0 minus sigma B, where sigma 0 is direct stress and sigma b is bending stress. So for no tension condition, direct stress should be less than sigma b. So in other words, we can say that direct stress should be either greater than or equal to bending stress. So we can write down sigma 0 should be greater or equal to sigma b. Now sigma 0 is equal to P by A. And sigma b is equal to m by z. So we can say that P by A should be greater or equal to m by z. Now m is the moment, which is equal to P into E, where P is the load and E is eccentricity. So I am replacing m with P by E. So I am getting Z by A should be greater or equal to E. In other words, I can say that E, that is eccentricity, should be less than or equal to Z by A to maintain no tension condition. In other words, I can say that this E is the E limit. Okay, so this E should be less than Z or Z by A. Z is the section modulus and A is area to maintain no tension condition. Okay, now let's discuss what is core or kernel of the section. So first of all, we will read Definition. The central part in cross-section of the column joining the points of E limit such that if the load acts within this part, there will be no tension included in the column. This central part is known as core or kernel of the section. So let's understand this definition by means of the figure. So here in this figure you can see that this is a rectangular section column and there are XX and YY axis. Now I am mentioning points of E limit in a column section, and by joining the points of E limit I am getting one central part of this column section. This central part generated by joining the points of E limit is known as core or kernel of the section. It means if this column section is loaded with eccentric load within this central portion, then there will not be any tension generated in a column section. Okay. So now let's move to the core or kernel of different cross section of the column. But before that, we will discuss few most important equation. Okay. So here, suppose the column section is rectangle in a shape, then area of the column section will be B into D. Ixx will be BD cubed by 12 and Iyy will be DB cubed by 12. Now for hollow rectangle section, area is equal to capital BD minus small bd. Ixx is equal to capital BD cube minus small bd cube by 12 and Iyy is equal to capital DB cube minus small db cube by 12. Now if column section is circular, then area of that circular section is equal to pi by 4 d square and Ixx is equal to Iyy is equal to pi by 64 d raised to 4. Now for a hollow circular section, area is equal to pi by 4 capital D square minus small d square and Ixx is equal to Iyy is equal to pi by 64 capital D raised to 4 minus small d raised to 4. Now let's discuss core or kernel diagram of different cross section. So we will start with rectangular section. So for no tension condition, E is equal to Z by A as we discussed in previous slide. Now EY is the E limit in Y direction. So EY is equal to what? ZXX upon A. Now ZXX is a section modulus in XX direction is equal to Ixx, which is moment of inertia in XX direction upon Y. Now for the rectangular section, Ixx as we discussed, it is BD cube by 12 and Y is a maximum distance of fiber of this column section from the neutral axis, which is equal to D by 2. So I am getting ZXX is equal to BD square by 12. Now area of this rectangular section is B into D. So if we put ZXX and A in equation of EY, then I will get EY is equal to ZXX upon A, where ZXX is equal to BD square by 12 and A is equal to B into D. So I am getting EY is equal to D by 6. It means E limit in Y direction is D by 6. So I mark 2 points on YY axis from this center point. Suppose it is point O. So I mark 1 point in positive YY direction, which is at a distance of D by 6 from point O, and I mark another point at a distance of D by 6 in negative Y direction from point O. Okay. Similarly, if I calculate, then I will get EX, which is E limit in XX direction is equal to B by 6. So I mark 2 points of E limits in XX axis. Okay, so from point O, I mark one point at a distance of b by 6. Okay, and another point in negative x-axis to mention E limit in x-axis. So if I join all these 4 points, then I will get this central portion of this rectangular section. This central portion of this rectangular section is known as core or kernel of this rectangular section. And if the beam is loaded within this central portion, then there will be no tension condition. Okay. Now let's understand the same thing by one numerical. Here we need to draw core or kernel of a rectangular section of size 300 mm by 200 mm. Okay, so width of this column is 300 mm and depth of this column is 200 mm. Now, as we discussed, Ex means E limit in x direction is b by 6, where b is 300, so Ex is equal to 50 mm. So I mark 2 points on x-axis. One point I mark in positive x direction, which is at a distance of 50 mm from point O. And I mark another point on negative x-axis at a distance 50 mm from point O. Okay, so these 2 points represent E limits in x direction. Now, similarly, if I calculate Ey, which is E limit in y direction, which is equal to d by 6. Here in our case, d is equal to 200. So, Ey is equal to 33.33 mm. Again, I am marking 2 points on y-axis. 1 point in positive y-axis at a distance of 33.33 mm from point O, and another point in negative y-axis at a distance of 33.33 mm from point O. Okay, so if I join all these 4 points, I will get core or kernel of this rectangular section. Okay, now let's move to another section, which is hollow rectangular section. Okay, so here the hollow rectangular section is given. For that, E should be equal to Z by A. Now, Ey is equal to what? Zxx by A. And Zxx is equal to Ixx by Y. For hollow rectangular section, as we discussed earlier, Ixx is equal to capital BD cube minus small bd cube by 12. And Y is equal to D by 2. So that Zxx is equal to capital BD cube minus small bd cube upon 6d. Now, area of this hollow rectangular section is capital BD minus small bd. So, if I put Zxx and A in equation of Ey, then I will get Ey is equal to Zxx upon A, where Zxx is equal to capital BD cube minus small bd cube upon 6d, and area A is equal to capital BD minus small bd. So, I am getting Ey is equal to d by 6. Similarly, if I solve, then I will get Ex is equal to b by 6. So, here in this figure, you can see that this central portion of this hollow rectangular section is represent core or kernel of this section. Okay. Now, let's move to another section, which is circular. So, here is the circular section. For circular section, again, E is equal to Z by A. So, we can say that Ey is equal to Zxx by A. Now, Zxx is equal to Ixx by Y. And for circular section, as we discussed, Ixx is equal to pi by 64 d raised to 4 and Y is equal to d by 2. So that I am getting Zxx is equal to pi by 32 d raised to 3. Now, area of this circular section is pi by 4 d square. So, I am getting Ey is equal to Zxx upon A where z-axis is equal to pi by 34 d raised to 3 and area is equal to pi by 4 d square. By solving it, I will get Ey is equal to d by 8. Similarly, I am getting Ex is equal to d by 8. So, by joining this, I am getting this central circular portion which is core or kernel of this rectangular section. Similarly, let's discuss core or kernel diagram for the holocircular section. So, again for holocircular section, E is equal to Z by A. So, Ey is equal to Zxx by A. Now, Zxx is equal to Ixx by Y. And for the holocircular section, Ixx is equal to what? Pi by 64, capital D raised to 4 minus small d raised to 4. And Y is equal to capital D by 2. So I am getting Zxx is equal to pi by 32D in bracket capital D raised to 4 minus small d raised to 4. Now area of this holocircular section as we discussed is equal to pi by 4 capital D square minus small d square. So if I put Zxx is equal to pi by 32D capital D raised to 4 minus small d raised to 4 in equation of Ey and A is equal to pi by 4 in bracket capital D square minus small d square, then I will get Ey is equal to capital D square plus small d square upon 8d. Similarly, if I calculate Ex, then I will get similar value capital D square minus small d square upon 8d. So here in this figure you can see that this central portion represent core or kernel of this holocircular section. Okay, so this is end of this session. Thank you.